Hello. This time we are going to find a conic section, which is a set of all points in a plane, the absolute value of whose distance from two fixed points is constant. So write that down. I'll try to straighten our screen a little. Okay. No can do. Oh well, pretty good. Alright, so I'll fill in the blank in a minute. So let's make some sense of what this might mean. You may pause to write it down and then rejoin me. So here's my two fixed points, focus 1, focus 2. And these foci are on a horizontal line, and that line has a name. It's called the transverse axis. It's horizontal in this case, as you can see. Alright, so let's find some points and see what this shape turns out to be. Let's say that I pick a point, I don't know, right there. I'll put an X. So distance from the first focus and distance to the second focus, I'll mark D1 and D2. Now this says the absolute value of their difference, the absolute value of whose difference, I think I left out a phrase. Yeah, that's not distance, it's difference. Sorry about that. Let's read it again. A blank is a set of all points in a plane, the absolute value of whose difference from two fixed points is constant. That makes more sense. So now we have this one, D1 minus D2, and that's some constant I'll call K. I can find another point, they may be out here, and D1 is longer, but so is D2. So D1 minus D2, it could be, I'm saying it is, the same constant. And if I find another point, could be out here like that, there's a point right in between the two where this minus this is the same as this minus this. And then there's some in this direction. But then we have this idea of the absolute value. So the absolute value means I can find a point over here where I have a short D1 minus a long D2, but because it's the absolute value, it means that this K can be constant. So once I go like that, I can switch directions or switch operations. I can do D2 first minus D1, and because I'm taking the absolute value, if this one is smaller, if D2 is, well, the way I wrote it, I made the smaller one. From here to here was D1. So D1 is the smaller one. D1 minus D2 would be a negative number, but when I take the absolute value, I get back to the same constant. So I'm going to have a similar shape developed over here. And perhaps you've seen one of these before. It goes like this. See if I can get it to show up a little better, maybe with a different color.
Party interruption. This is a reminder. Today is Chick-fil-A. If you would like to order Chick-fil-A for lunch, please bring your order to the office. Thank you.
Obviously, I'm taping at school, so. Alright, this is a figure. It has two branches. So here's one side, one branch, and here's the other branch. Two branches. It has a transverse axis. It has a center right in between the two. And there are some other values. This here is the vertex, and this is the vertex. So where one branch hits the transverse axis and the other one, you have your two vertices. Alright, and the values, switch colors again. The distance from the vertex here to the foci here is a value. And no, it isn't. The distance from the center to the focus is a value. See if I can put it up here, getting kind of crowded. So here's an arrow. So from the center to the focus, as well as this side, I'll just put it on one. That value is C. And the distance from the vertex to the center, this value right here, that value is A. Alright, so I put in a bunch of spots and labels, but what is it? It is the hyperbola. The hyperbola? No, the hyperbola. Okay, so the hyperbola looks like this. These are not parabolas that are facing one another, because the parabola will get fatter and fatter for all time, but the hyperbola is actually bounded. So I'm going to make a box here, and colors, colors, colors. Try white. So I'm going to make a box here, and notice one side of the box went through this vertex, the other side of the box went through this one. So my box is a rectangular one. If I connect the vertices of the box, I get that. And those are actually asymptotes. The way my sketch is, I'll show you what it should look like if those are asymptotes. The bend of my branches isn't wise. So it's going to go through the vertex, but it's going to get ever closer to the asymptote. That is what bounds this branch of the hyperbola. So we'll always get closer but never touch or cross these diagonals of my box, which are the asymptotes boundaries of the hyperbola. So let me get my green branch in nicely. Now you can see that side very well. And this one I should have bent closer to its boundary as well. Alright, so I'll clean that up a little bit. Alright. That's the theory for the hyperbola. And now the equation. Let's see if you can see it if I write it over here. The equation for the hyperbola, whose vertex is at HK, is going to be, so the vertex, Hector and Kyle, not the vertex, the center is at HK, Hector and Kyle, is going to look like this. X minus H, quantity squared, looks familiar, and that will be over A squared, minus Y minus K, quantity squared, over B squared equals 1. And that is the horizontal equation. And notice the only difference between that and the ellipse is what? What's the only difference? Let me see how well that showed up. Pretty good, pretty good. I'll just swing it over here. So that's the horizontal hyperbola. What's the only difference between this and the ellipse equation? The sign right there. So that makes it nice. And when it is going to be the vertical one, we'll have y minus k squared over a squared minus x minus h squared over b squared equals 1. Now you may, and hopefully remember, on the ellipse, these a was always the bigger number, and it was always under, and when the bigger number was under x, it was a, when it was under x, it was a horizontal, and when it was under y, it was a vertical. Now this one doesn't work that way. So kind of have to scrap your ideas on A and B, because in this one, the value, when the variable x is positive, notice there's a positive sign in front of it, then this one is horizontal. When the positive one is y, see this is the x became negative in this form, the y is negative in this one. So when the y is positive, it's vertical. So make a note of that. Alright. Positive x squared term is horizontal, and here positive y squared term is vertical. Notice the a squared term is always under the positive one, not necessarily the larger one this time. So things work a little differently, as you can see, in hyperbola land. Alright, I'm going to shut down this and see if I can do an example.